Hello and welcome back to the IIT PAL lectures on mathematics, and we have been discussing the binomial theorem and its applications, and this is the 7th lecture in the sequence. And so far we have been looking at the very first lecture was the binomial theorem, and after that we have been looking at a variety of problems becoming progressively harder, right. So, today's this particular lecture is hopefully going to be the last one, and given that the difficulty level has been progressively harder, today's problems are going to be pretty hard, if not I can't say that they are going to be the hardest of the lot, but they are going to be pretty hard ones. I am actually the IIT PAL lecture series is supposed to gear you up for a variety of entrance exams after class 12, and these are actual live questions, questions that have come, questions that might come, I do not know. Okay, this is just to prepare you. All right. So, my first example that I will work on is this. So, suppose the question is 2 power k n c 0 times n c k minus 2 power k minus 1 n c 1 n minus 1 c k minus 1 plus 2 power k minus 2 n c 2 n minus 2 c k minus 2 minus etc. The general term is minus 1, the last term is minus 1 whole power k times n c k n minus k c 0. So, this is the expression, and this needs to be simplified. All right, this is the question that you need to simplify this. How will you do it? So, first of all, observe the pattern. The pattern is as follows. So, if you take any general term out of these many terms, any ith term. So, this one here I is equal to 0, I is equal to 1, I equal to 2, etc., all the way till I equal to k. Right. So, if I look at the ith term, what do I see? I see, first of all, I see minus 1 whole power I, right, because the 0th term is positive, the first term is negative, the second term is positive, third is negative, etc., etc. Okay. So, minus 1 whole power I times 2 to the power k minus I. So, the first term is k minus 1, second term is k minus 2, 0th term is k minus 0. So, 2 power k minus I, and then n c I, right, and then so this n c I, n c 2 second term, first term n c 0. And then what have you got? You have got n minus 2 c k minus 2 over here. So, that will be for the second term n minus I c k minus I. So, this is the general term, and if you think about it, the net result is nothing but a sigma of this from I equal to 0 all the way till I equal to k. Okay. So, that is the final answer, the sigma. But let us observe this general term. Okay. You have done expressions where you had the product of two terms n c 0 n c r plus n c 1 n c r plus 1 and so on and so forth, right. In that situation, this exponent over here was the same as this exponent. So, here it is different, right. Here it is n c I n minus I c k minus I. So, this is not something very straightforward, okay. Not something very straightforward. It does not fall into any pattern that you know, okay, or have seen before. What do? You are going to expand the NCI n minus I c k minus I, expand it, right. If you do not know how to do it, expand it. So, NCI is factorial n by factorial I and factorial n minus I. And n minus I c k minus I is factorial n minus I by factorial k minus I and factorial n minus k. Okay? Great. So far so good. Now, obviously, these two cancel out, and this is great news, because when things cancel out, we all feel very happy. But you know something, it is not that straightforward. Let us look very carefully over here. I have got n factorial, and then I have got n minus k factorial. I have got I factorial and I have got k minus I factorial. What do you think is needed? Can I multiply and divide by k factorial, right? If I multiply this by k factorial, divide by k factorial, now what will happen? So, ordinarily you like cancelling. Here not only have I cancelled, I have also thrown in something from outside which you did not expect. Okay. Now, what is going to happen? I have got n factorial and I have got n minus k factorial and I have got k factorial. These three are going to combine, right. How do they combine? I get n c k, very good. And then I have k factorial, I factorial and k minus I factorial, and these three will also combine to k c I. Okay. Looks much simpler, or does it? At least I do not have n minus I c k minus I, instead I have k c I, and the first term is just n c k. Okay. So, now let us rewrite. I equal to 0 to k minus 1 whole power I 2 power k minus I times. So, what we have simplified so far is this portion n c k k c I, and what is nice is the following. This summation is happening when I is varying, right. As far as this varying thing is concerned, n c k is not varying at all, n c k is a constant, right. It is not changing as I is changing. So, in all the terms of this summation NCK is a constant. So, you can take it common. Look at the slate of hand that I have produced, right. I just threw in k factorial in the numerator and in the denominator, and lo and behold, I now have got something out of which okay. So, this is how my expression has simplified. Great. So, I have got NCK as common, and then I have got a summation. How do you tackle this summation? Now, you look at it, think about it. What is going on? Let us just write out, right. If you can't see exactly what is going on, let us write it out. So, I equal to 0 all the way till k. So, I have got k c 0 2 power k times minus 1 to the power 0 plus k choose 1 2 power k minus 1 times minus 1 to the power 1 plus k c 2 2 power k minus 2 times minus 1 whole power 2 plus dot 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 all the way till k, right. And what is this? This is equal to 2 minus 2 plus minus 1 whole power k, right. That is the binomial expansion of 2 plus minus 1 whole power k, is not it, right. 2. So, k choose 0, you do not choose any minus 1s, you choose all 2s. Then k choose 1, you choose only 1 minus 1 and you choose k minus 1 2s, and then k choose 2, you choose 2 minus 1s and k minus 2 2s, right, and take the expansion of this. So, this entire summation pretty much boils down to what I have over here, and 2 plus minus 1 is nothing but 1. So, 1 to the power k is nothing but 1. So, this whole answer is equal to n c k. All right. Was this a nice problem? This is a nice problem if you know how to do it, right. Why I am saying this is because of what I got in from outside, right. It is otherwise a very hard problem. If you do not know, if you do not realize by inspection that you need to throw k factorial in the numerator and denominator, this problem is going to make life miserable for you. However, with practice, right, with practice you will be able to see this and understand that you need k factorial on the numerator and in the denominator right away just by looking at the breakup. Okay. All you need is practice. The more you practice, the more you will be able to solve questions like this. Okay. So, it is an easy problem, but it is quite hard if you do not know the trick. Actually, all problems are easy till you know the trick. All right. So, after the last problem, let us try to do a similar problem in the same lines. You see, the more you do such problems, the more you practice, the better you will get at it, because a lot of these things are not very obvious. Okay. So, I will try to set up a problem that is very similar to questions that actually come in competitive exams like the IIT JEE. And one of the features, sometimes what happens is they give a paragraph kind of question. So, they set up a paragraph and then they have multiple questions about the paragraph. So, we are going to, I am just going to give an example, something similar, constructed a similar paragraph kind of an example. Okay. Also, a lot of times in the IIT, especially in the IIT entrance exams, the terminology used is slightly different. So, in the classes, in the lectures so far, we have seen NCR, right. This in our parlance means that you choose R objects out of n, right. This means factorial n divided by factorial R divided by factorial n minus R, right. So, a lot of times in the JEE exam, this notation is written like this. So, this is just an added piece of confusion, but do not get scared. This means nothing, this only means NCR. These are the binomial coefficients. Okay. So, let us try a problem. So, the problem is as follows. Let us define Sk is equal to 3 to the power k times 100 choose 0 times 100 choose k minus 3 to the power k minus 1 100 choose 1 99 choose k minus 1 plus 3 to the power k minus 2 100 choose 2 times 98 choose k minus 2 minus and then plus dot 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 this is the last term. So, it is minus 1 whole power k 100 choose k times 100 minus k choose 0. So, this is the setup of the problem. It says that Sk is defined as this, and then he says in the problem, he makes a further definition. He says that let Vk is equal to half to the power k times Sk, and he is also going to call this as m of 100 comma k. So, this is just his definition. Now, do not get scared, right. This is a function of two variables 100 and k. You see there is 100 inside. So, that is where the 100 is coming from. Do not worry about it right now. All right. Now, this is the paragraph setup, and then he comes to the questions. The questions that he throws. So, first he says that can you find this the value of this expression. Okay. And then the second question he is asking is can you find m 100 comma 49 plus m 100 comma 50. These are his two questions based on that paragraph. All right. So, we will try to work out these two questions, but first of all what you will notice is that this is very similar to our last problem, right. So, why we are doing this is just for practice. The more you practice, the better you will get at it. Okay. So, let us look at Sk first. So, Sk, and we will rewrite it because I do not really like this bracket kind of 100 0, I do not like it. So, I am just going to rewrite it in my own notation 3 power k 100 C 0 100 C k minus 3 power k minus 1 100 C 1 99 C k minus 1 and then dot 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 minus 1 whole power k 100 choose k 100 minus k choose nothing. All right, this is my rewriting of their question, and then let us look at the general term. So, this is a sum of many terms, right. It is the sum of many terms. Let us say 3 power I is okay. Let us say 3 power k minus I, where I goes from 0 all the way till k. Do you agree? So, there is 3 power k minus 1, here it is 3 power 0, right. So, when I is 0, I get 3 power k, then 3 power k minus 1, 3 power k minus 2, etc., all the way till 3 power k minus k, that is 3 power 0. Then this times there is a minus, it alternates plus minus plus minus. So, the 0th term is positive, next term is negative, and so on, times 100 C 0 100 C 1. So, the ith term is 100 C I, right, times 100 C k, then 99 C k minus 1 98. So, the ith term is 100 minus I choose k, k minus 1, k minus 2, k minus I. Fine. So, this is a general term which I have constructed, and this is a summation where I is going from 0 all the way till k. And just look at it, these two are not really equal, right, which means that I do not have any shortcuts at my disposal, and therefore, I need to break it up. How do you break it up? C I 100 C I is factorial 100 by factorial I factorial 100 minus I, and 100 minus I C k minus I is factorial 100 minus I divided by factorial k minus I times factorial 100 minus I minus k minus I. So, you get 100 minus k, and very nicely these two cancel out, but then you are left over with factorial 100 minus k, and then naturally you say I need a factorial k as well in the denominator. So, if I need a factorial k in the denominator, then I should have another factorial k in the numerator, right. And now you regroup. So, I have 100 C factorial 100 minus k and factorial k, and this is 100 C k. And on the other hand, I have factorial k, factorial I and factorial k minus I. So, what is this? K C I, very good. Okay. So, that is what I have, and then the remaining part can be thrown back in. All right. So, this is the story so far. Now, can we work with this? So, Look at this 100 C k. This 100 C k is a constant as far as this summation is concerned, because in this summation I is changing. So, when I is equal to 1, I equal to 2, I equal to 0, 100 C k remains exactly what it is, because k is a fixed number. Okay. So, therefore, you can take it outside the summation. So, you can rewrite it as 100 C k times sigma 3 power k minus I minus 1 whole power I k C I, where I is going from 0 all the way till k. And now, tell me what this is. What is this boxed thing, this whatever I pointed out, this sigma 3 power k minus I minus 1 whole power I k C I. Can you identify this? K C I means out of k you are choosing I, and then you have chosen I minus 1s, right, and you have taken k minus I times 3 to the power k minus I. So, k minus I times you have chosen 3. So, it is as if you have got 3 minus 1, 3 minus 1, all of these k times, right, and out of these k minus I times. So, there are k of these, and k minus I times you have chosen 3, and I times you have chosen minus 1, right. And then how many ways to do this? That is k C I, and therefore, this entire thing boils down to 3 minus 1 whole to the power k. Okay. So, you need to be able to make this deduction, look at this and figure out that this is 3 minus 1 whole to the power k indeed. Okay. Once we are done with that, the next step is very straightforward. The next step is that therefore, S k is nothing but 100 C k times 3 minus 1 whole power k, which is 2 to the power k. All right. Okay. So far so good. Now, let us go back to our question. Our question was compute S k S 100 minus k sigma of that from k equal to 0 to 100, and all that I have done so far is I have figured out what is S k. So, S k is this, and S 100 minus k, what is that going to be equal to? It is going to be 100 C 100 minus k times 2 power 100 minus k, all right. And then if I do a sigma of that, this was my question. What do I get? I get sigma 100 C k 100 C 100 minus k. Mind you, these two are equal, 100 C k is equal to 100 C 100 minus k, just by the way, reminding you, times 2 power k times 2 power 100 minus k, which is nothing but 2 power 100, and 2 power 100 can jolly well come outside this summation. Is this familiar now? Can you do this summation? Sigma k equal to 0 to 100, 100 C k times 100 C 100 minus k. If these two are equal, they are equal, right? They are. Then this is also equal to Remember, we had done something like this a long time back, right? A few classes back we had done this. Even if you do not remember, that is okay, right? The way we had done it, see, that is the beauty of mathematics. You do not always have to remember everything, you can work it out. It is not very hard, right? All you have to do is remember how to work it out. So, this is what we had done, x plus 1 by x whole power 200. Okay. And then we were looking at the term independent of x in this result, right, x plus 1 by x whole power 200. The term independent of x in this is the middle term, where I have got x power 100 times 1 by x power 100, right, that is the middle term, and that middle term is 200 choose 100. Okay. Now, here you expand this whole thing term by term, and then for every x you need to look for a 1 by x over there. So, for example, if this breaks up in, if you have x power 100 over here, you need 1 by x power 100, right. So, that is C 0 times C 100 plus C 1 times C 99 plus C 2 times C 98 all the way down, right, and it so happens that C 99 is equal to C 1, C 100 is equal to C 0. So, you get back this, or you do not even have to get back, this is the same as this, right, 100. So, k equal to 0, 100 C 0, 100 C 100, then 100 C 1, 100 C 99, 100 C 2, 100 C 98, and so on and so forth. Okay. So, this sigma is nothing but 200 choose 100. So, that is your final answer. Okay. So, this is the first part of our paragraph, and then what we are going to do now, we are going to try working out the second part of the paragraph. And what was the second part of the paragraph? The second part of the paragraph was, can you compute m of 100 comma 49 plus m of 100 comma 50, where m of 100 comma k is half power k times s k. So, m of 100 comma k is half power k times s k, right, and I have worked very hard to figure out that s k is 100 c k times 2 power k. And the great news is that half power k cancels out with 2 power k, and you are basically left with 100 c k. So, that is m of 100 comma k, 100 c k. It is nothing much, nothing spectacular, right, it is just to throw you off, all right. And then what is his question? The question is, what is m of 100 comma 49 plus m of 100 comma 50? And now you can do this, can't you? M of 100 comma k is nothing but 100 choose 49 plus 100 choose 50. Okay. How do you do this? Are you going to start calculating 100 C 49 plus 100 C 50? I hope you do not, right. This is even the very powerful calculators will not be able to calculate these large numbers. These are very large numbers. So, do not even think about calculating. Okay. There must be a better way. Look at them, they are adjacent terms in the binomial coefficients, right, and they remind you of the Pascal's triangle. Right, this was your Pascal's triangle, right. This is so the way it is done is that if I want to find out this particular term, this particular coefficient is the sum of these two. Okay. This one is the sum of these two, right, and these are all ones. So, if I want any term over here, I look at the two terms on top and those two will add up to give me that term. That is your Pascal's triangle, which means that 100 C 49 plus 100 C 50, this is the 0th layer, this is the 1th layer, 2th layer, 3th layer, 4th layer, like this the 100th layer, right. If I look at the 100th layer and pick two terms, then the sum of them is going to be the 101st layer, choose. So, if this is 49, this is 50, then this is going to be 50. Okay. And of course, 101 choose 50 is also equal to 101 choose 51. So, this is just for your own, I mean, if required, right. A lot of times these questions are multiple choice and maybe 101 C 50 is not one of the choices, but 101 C 51 is one of the choices. Then you say 101 C 51. So, whatever is required. All right. So, this completes this particular problem and then we will go to the next one. So, as you see a lot of these techniques is about practice. The more you practice, the easier you will be able to reach the easier it is going to be to solve the questions. I will give you one more. So, let us look at the following. Let us do a product of 1 plus x, 1 plus x squared Okay. So, you have got all of these and let us say I multiply them. Right, and after I do this multiplication, I expand it up and I write it as a 0 plus a 1 x plus a 2 x squared plus a 3 x cube plus dot dot. Now, you have got many questions. Question 1 is how many terms are there? In this expansion. Question 2 is show that coefficients equidistant. So, for example, the first term is a 0 and the last term is let us say a capital N, x power capital N. So, a 0 and x n, a n, a 1 and a n minus 1, capital N minus 1, a 2 and a capital N minus 2. So, these are coefficients that are equidistant are equal. And 3, sum of odd coefficients is equal to sum of even coefficients is equal to n plus 1 whole factorial by 2. So, you have to prove these three. First question you have to answer and the remaining two you have to prove. You want to try? How many terms are in this expansion? So, of course, it depends on the value of n. So, let us say n is 2, right. If n is 2, then I have got only the first two terms 1 plus x and 1 plus x squared, right. And then I will get a term corresponding to x cube, I will get a term corresponding to x squared, I will get a term corresponding to x, and I will get a term corresponding to 1, right. So, I will get x cube, x squared, x and 1. So, 4 terms, right. So, it is basically this plus this, right, 2 plus 3 minus 1 gives me 4 terms. Is that okay? All right. Let us say there are 3 terms 1 plus x, 1 plus x squared, 1 plus x squared plus x cube, right. So, you will have the minimum term is going to be with units and the largest term is going to be with x squared x cube, that is x power 6. So, you are going to go all the way from units to x power 6. So, that means you will have 7 terms. Let us say you have got the next one x power 4, right. So, you will go from units all the way till x times x squared times x cube times x power 4. So, that is x power 10. So, 11 terms, right. N such, that means how many terms? So, you are going to go from units all the way till x power 1 plus 2 plus 3, x power 1 plus 2 plus 3 all the way till n, and that is equal to x power n into n plus 1 by 2. So, you will start from units x power 0 and reach all the way till x power n into n plus 1 by 2. That means, the total number of terms is going to be n into n plus 1 by 2 plus 1. So, this is the number of terms. Fine. And of course, capital N over here I have written it as capital N. This capital N is going to be n into n plus 1 by 2. Very good. Now, can you show that coefficients equidistant from beginning and end Can you show that the coefficients equidistant from the beginning and from the end, they are equal? How will you do that? It is not too difficult, right. All you have to do is work out one sequence with x and one sequence with 1 by x. So, for example, if 1 plus x times 1 plus x squared plus times dot 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 times 1 plus x squared plus dot 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 x power n, if this is equal to a 0 plus a 1 x plus dot 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 to a capital N x power n, then what will be 1 plus x power minus 1? So, replace x with x power minus 1. That will automatically be a 0 plus a 1 x power minus 1 a n x power minus n, right. No surprises there, right. But then you can simplify this and write it as, you can take x power minus 1 common, x power minus 2 common, x power minus n common, and then net you are going to get x power capital N times 1 plus x plus x squared, or rather x squared plus x plus 1, x power n plus x power n minus 1 all the way till x squared plus x plus 1, right, and that is going to be equal to x power n times a 0 plus a 1 x plus minus n. Okay. And here you will see that a 0 times x power minus n has therefore got to be equal to a n times x power minus n, and a 1 x power minus n plus 1, this particular term has to be the second last one, this last one has to be the first one. So, a 0 has to be a capital N and so on and so forth. Okay. So, terms equidistant from the beginning and from the end are therefore equal. Then the last question, can you show that the sum of the odd coefficients is equal to sum of the even coefficients is equal to n plus 1 factorial by 2? Easy stuff. How do you work out sum of odd coefficients equal to sum of even coefficients? Do you remember? We did it for the original x plus 1 whole power n, right. We had done something, we just plugged in x equal to minus 1. Here plug in x equal to minus 1. What happens? If I plug in x equal to minus 1, the net answer becomes equal to a big 0, right. If I just plug in x equal to minus 1, the net answer becomes equal to 0, which means 0 is equal to a 0 minus a 1 plus a 2 minus a 3 plus dot dot dot, right, and therefore, the sum of the odd terms is equal to the sum of the even terms. Very good, but I do not have a value, he wants a value. The value is also possible. In that case, plug in x equal to 1. Remember, we had done this for the basic setup. So, what these questions are trying to do is trying to test your understanding, right. How did you work out those problems, right? It is a repeat of that. So, plug in x equal to 1, what do you get? You get 2 times 3, next one will be 4, 5, 6, n plus 1. Right, that is what you will get if I plug in x equal to 1. And what will I get over here? I will get a 0 plus a 1 plus a 2 plus a 3 plus a 4 all the way till a n. Now, half of them are equal to the other half of them, right. So, 2 times the sum of the odd terms. So, the sum of the odd terms is equal to this divided by 2, and what is this? This is n plus 1 factorial. So, there you have your answer is there, n plus 1 factorial by 2. All right. So, we have basically covered in the last 7 lectures a variety of problems based on the binomial theorem, and at the end of the day the binomial theorem always has to be thought of in terms of the basic structure. The basic structure is you have got many terms and then you are choosing, right, to multiply, right. That is, you always have to work with that perception when you work with the binomial theorem. Okay. So, we will stop here, and we are actually going to extend this to techniques beyond integer n. So, in the next class we are going to look at an extension of the binomial theorem. This is not an ordinary extension, there is a leap of faith, and the leap of faith is that the binomial theorem somehow is still going to work even when n is not a natural number. So, we are going to work with that and problems based on that starting from the next class. Okay, thank you.